Hello everybody, welcome to another episode of Undercool. For those of you watching the video, you'll notice our third seat is mysteriously empty today. Steve and I were feeling nostalgic for the old days when it was just the two of us yapping at each other, and we thought it'd be fun to do an episode without a guest so we could just have a conversation about education like the good old days.
Absolutely. And actually, this has come about because one of the things we've started to do in our recent podcasts is bring in people from industry who've had successes with improving sustainability through materials design. Let me just back up a little bit. Part of that is because I've gotten involved with this organization called Engineering for One Planet.
Right.
And it's a Lemelson-funded organization that has a very noble mission. They want to inject sustainability topics into all engineering education across the country. So naturally they partnered with ASEE because that's one-stop shopping.
Yep.
All societies are represented there, and who knows more about teaching and curriculum development than ASEE. And so it's been running really well for several years. They've made great strides. But most of the effort has gone into introductory courses because a huge number of the people who are ASEE members are lecturers and folks who teach the, large introductory lectures because, that's a high payoff in terms of benefit.
Right, especially if you're doing any sort of funded work, you want to be able to demonstrate impact. And it's a lot easier to demonstrate impact with a class of 200 than a class of 20. So
I come along, and I'm not an engineering education researcher, and I teach upper level materials courses. And I noticed they didn't have a lot of really good detailed content for higher level courses or even graduate education. And at first they told me that, that's not important. We're trying to do things that are at the low level. But I kind of think it is important.
we can do both.
We can do both. They've developed a framework because it's an engineering, education, research-driven thing. We don't have those frameworks in most science or engineering, but that's because we have something a little different. We have things like laws, Newton's law, and laws are inviolable. So laws are a framework, but we spend our time as researchers in science. If we want to get something published, we better be breaking the frameworks and adding to our laws by observing things that we can't explain, so we have to create new science to explain it. There's a bit of a mismatch. But within the framework, which is really nicely done, by the way, they really cover many salient areas. I'm not going to talk about it. You can go on to eop.org, engineeringforoneplanet.org, and find it. But what really stuck in my side was what they did with materials.
Oh no.
They have materials as one of the hubs of this framework, but all it is material selection. And material selection is really awesome. And Mike Ashby, I've gotten to know him for years with the North American Materials Education Society.
Yep.
I mean, he's so famous, they even named a plot after him. How cool is that? The Ashby plot.
That's what we should all aspire to as scientists.
Absolutely. Plus, he's an amazing person, brilliant guy, and has made massive contributions to engineering. But I think he'd be the first to agree with us that material selection is just the first step. It gets you in the right direction. Ultimately, to solve a problem, you need to design your own material for an actual application. It's not material selection that material science and engineering brings to the table. It's materials design or process design to create a material that actually works for whatever the application is. You don't just go choose a solar cell material using the Ashby software. It'll get you close. It'll tell you probably you should look at semiconductors. And all of those solar cells that are now on our roof that cost very little money, that are 22, 23% efficient, that's 80 years of incredible basic research at universities, at industries like what Bell Labs did and what lots of these other companies are doing. And it's a highly refined process. So how do we bring materials design, which is different than engineering design? It's similar, but materials design really uses everything our students learn about thermodynamics, about structure, about kinetics. Those are our tools, our guide rails, if you may, that allow us to fool Mother Nature and make things that don't exist in the natural world.
Right. Convince atoms to do what you want them to do,
Exactly.
not what they would normally do.
So Tim and I have been doing this podcast, and I said to Tim, I said, what if we bring in some guests who can, not only talk about materials education, what they're looking for in students, how skills like teamwork and communication are important in the industrial setting, but also ask them things like, what have you done for sustainability lately?
Mm-hmm.
And so we've already been very successful. I think one of the great examples is our recent podcast with Paul Krajewski, where he talked about the hemming process and replacing steel with aluminum on the outfacing panels of cars. And he used the example of the Chevy Suburban. And it sounds easy. You just go find a lighter alloy with the same strength and you're done, right? Until you want to crimp it to make it hold on to the underbody. And then aluminum cracks. Mm-hmm. So he told us how they solved this problem, and it works. This is how all of these are done now, and now every car company does the same thing. It was a very important bit of engineering design to do this, but the engineering design was all about understanding the aluminum alloys they wanted to use, how to get rid of precipitates and GP zones so you could bend it without cracking. But he left a lot out of that little 5-minute segment. And we'll play that little 5-minute segment so you can see what we're talking about right now. And after you watch this, come back and you'll see what's missing in that 5-minute segment. So take a listen.
A lot of my career has been involved in lightweight materials, especially when I was a researcher before I moved into some of the leadership roles. So one of the first ones that I worked on was a aluminum heat treatment to eliminate cracks. And super fun, and again, this kind of tells the story of leveraging technology from other industries and see how they might apply. So I brought a couple of examples here. This is a sample from a ladder. And in this case, you've got the rung of the ladder that you would hold as you walked up, and then the things you may step on the side of the ladder. And the interesting thing is the way that these ladders are made. They're aluminum. This is aluminum 6061 T6, heat treated, not very ductile, very strong. But when you put these two things together, what they do, if you could look and maybe take some pictures and show afterwards, they're crimped. And you essentially take this rail, put it through a hole, compress it, and that's what locks it in place. If you tried to do that with the T6 material, it would crack. Wouldn't work.
Sure.
So what the aluminum ladder industry had developed was a heat treatment to enable that to dissolve the precipitate structure, essentially form it in a W temper, and then I can compress it, and I could make that very complex bend with no crack. So we had looked at this technology and found a problem that was going on with many of the parts. At this point, we were making an aluminum liftgate, so the back end of the car in our Suburbans, and we're challenged to, when we were putting those vehicles together, there's a term called hemming. You take an outer panel, so what you see on the back of your car, with the inner panel that holds all the stuff that's inside of it, and they're hemmed together. So the inner and the outer, and it's crimped 180 degrees over the top. with aluminum, that would often crack. So leveraging that technology, studied it in the laboratory in R&D, developed a heat treatment that for 400 degrees C, for 0.4 seconds, we could dissolve away, in this case, this was a T4 material, dissolve away the GP zones and unstable precipitates clusters that were there, and essentially get rid of the cracking. So you could see on the edge here, with no heat treatment, totally cracked. With the heat treatment, totally went away.
And we'll have a photo of that on screen for people to see.
So this is another one of those messages for kids. You got to be able to market and talk about it. So see this word on the samples that we used, ATIM, aluminum treatment for improved manufacturing. You needed a buzzword. You needed to be able to go and say, here's what we're marketing. Went into the plants, found the problem, and then was the challenging part. I could do all this in the lab. I had to figure out how to do this in a manufacturing environment on our parts. So we worked with somebody outside. We built a fixture. We had an induction coil with a flux concentrator that allowed us to take that heat treatment super local. So it was like a 3 millimeter section around the whole periphery of the part with that rapid heat treating. So there's no buckling, no distortion, and we're able to make that work in production. So super fun application.
In the process of working that out, how much of that work was experimental? Was there modeling involved? Were you like doing kinetics calculations, or was it all build it and try it?
No, so it was a little of everything. So I started with an old school salt pot, right? And we'd put them in for 1 second, 2 second, 3 second, 4 second. And the interesting thing is when you look at these, so they're called retrogression heat treatments. They've been used in the aerospace industry for a long time in 7000 series, but we used them here in the 6000 series to dissolve away the precipitate structure that's there. If you look at it, every temperature has a different time temperature curve for hardness, right? Go to higher temperature, I could dissolve things faster, I can get a different, it's essentially a well in the curve. So use the kinetics to kind of predict what that is, look at, what the key, in this case, we were looking for the well. So when everything was dissolved, you could look at the time to dissolved as a function of the temperature, come up with a nice equation to predict it, know what you needed to be, what could I do from a manufacturing perspective, what hardness I need, create that model, and you could do all that work. So you took that stuff from the lab, then be able to predict it, and then apply it in the plant with an induction heater and a flux concentrator. Yeah.
So coming back to this as a materials educator, before we give away our secrets here, part of the reason this is so important is that in stories like this one, this problem wasn't solved by taking something off of a shelf that already did what was needed, because what was needed didn't exist on a shelf. And this is something that we need to convey to our students, partly to attract new students to the field of materials, of course, but also to help our own materials science and engineering majors understand why they're doing what they're doing. They're here to create the things that don't exist yet and to use what they learn in thermodynamics and kinetics and structures to say, oh, I can work around what's on the shelf, change it to be the way I want it to be, maybe even in a tricky time-dependent way like this crimping project, and apply that information to create new solutions that can't just be looked up and bought as they are.
Absolutely. So as you saw in the little video, he didn't talk about what precipitates and GP zones do that make the material brittle. But we learned that in our mechanical properties courses because there's these pesky little things called dislocations that if there are precipitates or GP zones that get pinned, and that makes it much harder to deform the material and makes the material far more brittle and susceptible to cracking. And he also didn't talk about any of the kinetics of what temperature does to dissolve those precipitates. How did he know that 400 degrees C was a good temperature and for how long? Well, we teach our courses on kinetics about that. And how did he know what the thermodynamics that are driving all these processes are that are the underlying, physics of what's happening? So we realized that wouldn't it be fun to have a team of students watch this video And now you choose what course you're in. Say you're in a kinetics course. You can ask the students to prepare a presentation where they explain all the kinetics that are going on and how they would approach actually doing the experiments to figure out the time and temperature needed to do this. That's step one. Then you can give them a different problem with something that hasn't been done yet and ask them to apply what they just learned. Now they have a, dare I say, framework to approach a new problem. And they'll actually learn the way we've noticed students learn best these days. Sadly, it's not like how Tim and I learned. Sadly, they don't read textbooks. They use it as a reference. What? Textbooks.
Can you run that by me again? Okay.
But they do watch videos. They watch YouTube. Right. And they're very proficient with using artificial intelligence, ChatGPT. And so this same little example, in fact, we're going to be asking him if he'll do this, could be used by Professor Wenhao Sun, who talked about vibe coding, to write some MATLAB scripts to actually model what he was doing. Mm-hmm. And you could use that in a kinetics course. Or you could model the thermodynamics of it, and again, do modeling, because that's a nice tool to have. Frankly, when Paul did this first thing, artificial intelligence didn't exist. They might have modeled it, but it's, that was a while ago that he did this.
Right, and so it's this back and forth of get in the lab, build some stuff, measure its properties, right, calibrate your model, do some calculations, get back in the lab, and that's a completely fine process.
But now we can accelerate it with computational.
And that means you can do it in a class instead of it being a research project.
Right. And so this could even be used in an intro to materials course. You just have to scaffold to help them be able to do what they're going to do so they're aware. But, we just think this is kind of an interesting process. Something that, as Tim pointed out, maybe you can tell them what Ashby did in one of his books, but it's a textbook. But now we might be able to do it with these new methods. So what did Ashby do?
Well, before we get to that, there's another huge affordance of having these video stories collected. They're incredibly motivational. Even our own students in our own classes often ask, why am I learning this stuff? Why am I learning about nucleation? Why do I need to learn about the critical size of a nucleus?
Pinning dislocations.
Right. Yeah, why do I have to learn about dislocation pileup? Yeah. It's just numbers, it's just math. So we have a story, we have a real tangible engineering example of a professional engineer who used this stuff in their own work to solve a legitimate problem for a client. And that gives the students the reason to say, oh, this is why this is useful. And then they get to apply it to themselves, exactly as you said. Right. Let's try to extrapolate this to a new problem and see if it applies there as well. So that motivation piece is so huge because students rightly ask, why am I learning this stuff? And we should be able to answer that.
And so that was one example. And I think it's got a very rich application domain, so to speak. But something else that's occurred to us is that when you get these problems that have been solved by industry that are willing to talk about it, so usually these are problems that were solved a few years ago, there are also problems that allowed the companies that did the work to make money. Because the best sustainability solutions are the ones that make economic sense. Mm-hmm. Just because we can turn lead into gold, and we can, we can't do it cheaper than the price of gold, as expensive as gold is today.
We're still a few orders of magnitude off there.
That's right. And so it's important to explain to students how valuable it is to help your company make money while also meeting your sustainability goals. And so that means making a better product for your customer, a product that's more sustainable, and then it's just win, win, win. So these are the examples. The last podcast we published, the one that was right before this one, we talked to Joel McDonald, who's the technical director for mobility products at Dow Chemical. That's a huge sector of Dow Chemical's work. And he told us about something that Dow Chemical did. They found a way to recycle polyurethanes, something nobody knew how to do before. And they didn't just, so they dissolve it in these chemicals and go through processes. They have ways to sort, to throw out the stuff that's no good, to keep the chemical precursors that are good. And then they develop new markets for it, and they've published this. We'll put the links in the show notes to some of the places where Dow talks about this, including their first product was they used it for making mattresses. You know, all those foam mattresses that get shipped to your house and they blow up in your bedroom and you wonder, how am I going to get it out? But they did that. And now they've started a project with some pretty high-end automotive companies making car seats out of all the foam of old cars. So that's an incredible circularity, and they found a way to do it that actually makes them money and creates a new market.
I mean, mobility is there's a big trend in that space. So they're trying to figure out how to recycle cars, and that's a big issue. And if you look at a car, the metal today is actually fairly easily recycled. There's a fairly high percentage of that that's returned to the supply chain. But the plastics, the foams, all of that, much less so. And so the next, there's a big push in the EU right now to drive up the numbers. I don't know if they've settled or landed on a final number yet, but a lot of the sort of groups that we talk to over there are asking us questions around how to achieve that. So one of the innovations that we've recently been pushing in Europe is an approach to recycling polyurethane foam seating so that it can go back into the supply chain. So that one's like almost like a chemical recycling path. So you're taking that polyurethane foam and you're bringing it back to the original polyols that are used in conjunction with isocyanates to produce a foam. And so we've gotten to the point now where we can basically complete the circle. We found a good way to do it. It's a complicated system too, because you can imagine you're taking about a seat, you've got the heating elements in it. There's a lot of electronics in there now. It's not just simply, there's adhesives of other chemistries. Again, it's kind of like the multi-layer film problem. You've got all these different chemistries, materials coming together. So it does take some careful touch to get to what you want, but we worked on that part of it, like the supply chain piece, and then Dow's worked on the chemistry side of it to get back to those original building blocks so that we can reincorporate them into the next round of seats that are produced in vehicles. And so we're partnering with major automakers to do that, and also seating providers like Adient is one of our collaborators there, and Jaguar Land Rover in particular is an automaker that's driving that. So definitely a big push in Europe. We talk about it all the time over there to try to increase that recycled content that goes back into the car. Then I think that number one is like polyethylene, the next is like polypropylene, I think PP, and the next is polyurethane as the plastic materials, polymeric materials inside the vehicle. So trying to get some progress on both of those would be significant.
And that's the hardest part of many of these challenges, is not making it work once in the lab for a few molecules.
Right.
It's for making it work in a way where it's scalable and where it makes sense for the public, not just for the researcher. And this is something that in my freshman class, let's get back to Ashby here, is something that we pitch really hard. You can do good and make money at the same time. Right. That's part of the beauty of being an engineer. You can create solutions that people want and are willing to pay for that can also improve their quality of life. And that's really what we're about here. So when teaching this stuff with Ashby's textbooks, which I do use in the course, he has some really nice case studies.
Right.
And one that I just did with my class is about biopolymer production. And so it's a great compare and contrast example. We can make polymers from petroleum, we can make polymers from corn. What are the advantages and disadvantages of each approach, both in terms of materials performance, economic costs, environmental impacts, and so on. And the students are really excited about this. I asked them at the start of the semester, what are you guys excited about this semester? And they said, we want to do case studies. We want to talk about real engineers and what they actually do. Awesome. So let's give it to them.
Yeah.
And then I tell them that they have to read 20 pages in a book. They're suddenly less excited about it, which I can't fathom. But the youth of today.
But perhaps
so how do we reach them?
If they watched a video of a real engineer who has actually solved the problem and talks about what their company did and what the impact is. Hopefully that will motivate them. Hopefully these short little clips are inspirational, because as you know, that's the hardest thing about education.
If you can make someone want to learn, they'll find a way to learn.
The reality is that students will not learn anything if they just sit and watch. They have to do it.
That's right.
And it's to the point where psychologists even talk about this thing called the Feynman effect. And it kind of reminds me of, we went to one of the NAMES meetings, I think at Stanford, and the CEO of ANSYS was there.
Oh, yeah.
And he gave this whole talk about, with computation and video, we're going to get the world's best instructors, and we're going to film them, and we won't need universities anymore. And of course, he doesn't know much about engineering education, or education for that matter. And he missed out on something very important. You might be entertained by these videos, but you're not going to learn anything, because nobody learns unless they do the hard work of doing it themselves. There's only one teacher that's going to be important, and that's the person themselves. They have to teach themselves. We can be guides. We can push them in the right direction, create exercises to make them stretch their skills. And the psychologists talk about these great teachers. They call it the Feynman effect. I didn't know about this till a few years ago, but it was fascinating. So, we all know Richard Feynman was an amazing communicator. There's even an AI video series with fake Richard Feynman. It looks just like him, talking about why, aliens will never get here. And it's not only because of the large distances, but also because of the fuel. They'd have to make their whole spaceship out of fuel, and they'll never get back. At any rate, Richard Feynman was famous for saying, you don't really understand something unless you can teach it to a 5-year-old. And there's a lot of wisdom in that. But that the converse is not true. If you can explain it to a 5-year-old, that doesn't mean the 5-year-old will actually learn it. They will be entertained and understand what you said. And the reason psychologists were interested in this, Feynman was really famous for explaining stuff, but he taught physics at Caltech. And they taught several sections of physics to all of the engineers at Caltech. And they had all these, Nobel Prize winners and stuff teaching engineers physics. And then they had a common exam. Well, where do you think Feynman sections did?
Probably at the bottom.
They were at the bottom. They were the worst in terms of their performance on an exam. And we can get into whether an exam means anything or all of that. But the reason that they were the worst is, after hearing Richard Feynman explain physics to them, they thought they understood it, and they stopped doing homework and problems. And they didn't put in any hard work. And so when it came to the test, they really didn't have a clue how to do it. They were completely bamboozled by the skill of a great orator.
Which is funny, because most people don't make that same assumption about physical skills. You watch a figure skater at the Olympics, you don't just assume that you know how to figure skate because they make it look easy.
Right.
But somehow we convince ourselves that for cognitive tasks, it must be that easy.
That's right. Yeah, I think Eric Mazur famously said, if you want to run a marathon, you don't sit in front of the TV eating popcorn, watching marathon runners run.
That's right.
And we all know that. But why do you think you can solve engineering problems by watching an engineering professor solve problems on the board? And in that moment, you might think you understand everything that they did, but that doesn't mean you can do it.
That's right.
And that's a big disconnect. So back to our little scenarios, this thing Joel did, he showed how Dow Chemical, found a way to recycle polyurethanes, something that before this could only be used to chop up to make, chips
playground
for playgrounds,
rubber.
right?
Yeah.
And you hear that for all these different kinds of polymers, and you wonder, how many playgrounds do we really have that need chips? And but they found a way to dissolve this stuff chemically and turn it into these products. But again, during the short description, Joel didn't tell us how they did it. He didn't tell us the science behind it. He didn't talk about the economics, something else we learned from his podcast. He didn't talk about how Dow protected themselves with patents. And so you could use this little clip to ask a polymer course to look up some of this information and explain the chemical reactions that went on and the kinds of polymerizations that needed to be done, and then how they tuned it to make their products of either seating or a mattress. Because you know, when you sit in a car seat, it's not as soft as a mattress, because it would be a really weird feeling to be sitting on a mattress in a car. And you don't want to sleep in a car because it's much harder than your mattress. Although we've all done it, it's not a pleasant experience. And so it's a great opportunity for a course in polymers, but it's also a great course in a design course if you can say, take this and go do some research with the patent office, search the patents and find the patent trail so you understand how they protected themselves and kept their IP, right? And that's not even, is that sustainability? Well, yeah, because without that, the company couldn't make money and it wouldn't be a useful project. So sustainability takes many roles, and the same clip can be used in very different classes. And of course, this same clip, if given to somebody in a chemical engineering department, could talk about how do you scale this up into a big plant, right? We don't do that in material science, but it could also be used in a mechanical engineering department. I can't come up with examples of how to do it in those departments, but we're going to try to come up with lots of case studies as examples in material science. And later this week, Tim and I are going to be at the TMS meeting, and we're going to be asking for help from the entire TMS community to, those of you listening, to not only help us take these clips and turn it into curriculum, but to suggest guests to us that we could have on the podcast. I think it's best for these if we find people from industry.
That's right.
It's rare that someone in academia is at that level where they've actually made economically viable sustainability impacts. It can happen. Certainly some faculty who have companies and all of that, but that's a different sort of task. So we're really hopeful that we get lots of other suggestions, and at any rate, I think this is going to be fun for us to do, and it should add to the curriculum.
So, two other thoughts occurred to me while you were describing Joel's description of the chemical recycling product. Another thing that this enables us to teach, maybe in a way that is not as obvious with the textbook, is there's so much critical reasoning and critical inquiry skills around this as well. As you were listing out all the things he didn't say, students are so used to just accepting what they're given. A person of authority has handed me knowledge, I shall receive it. And we want them to do the opposite, right? We want them to say, what about this? What about this? What about this?
Right.
And you simply can't get all of that in a 3-minute video clip. And so it creates the opportunity for students to say, what about all those other things? Which is exactly what we want them to do. And that's especially important in sustainability because there are so many unknowns, there are so many values with huge error bars, and there's outright misdirection as well. And we need students who are able to see through that in the information that they're given in order to find the real truth, dig deeper where they need to dig deeper, and to try to make sense of all these things.
Absolutely. So we're kind of hopeful that in the next 2 or 3 years, we're going to be able to put together maybe 100 stories like this across all areas of material science. And if we could get that far, maybe we could even consider this like a textbook, a set of resources that serves the purpose of what textbooks did 20 years ago. And of course, we're not going to try to make money on this. We're going to make this all freely available. So, those of you who might have known me knew that I tried to create an open source textbook project for materials science, along with Mark DeGraff at Carnegie Mellon. Mark's told us that he'd be willing to talk to us about the future of the textbook. But the truth is that project ended because Mark and I realized textbooks are passé. That's not what the future holds. Not with all the wildly available YouTube videos. COVID had us produce massive numbers. Everybody had their course on YouTube, and all that stuff still exists. Do we really need another person lecturing about, what phase diagrams and the lever rule? How many, there must be hundreds of lever rule videos out there. And what's important is that should the professor be the one just lecturing about it and reproducing what's in the video, or should they be the guide for student teams, having them work the way they will work in industry or even in academia with a team of people, doing what Tim mentioned, questioning things, asking questions, answering them, being resourceful, and using AI, which is here to stay no matter how much we might hate it, because it is amazing. So it's this love-hate relationship that's already started with AI. And if, it's incredible what AI can do. But just remember, AI is only copying what's been out there. There's a lot of stuff out there, so it's really useful. And but it still is not going to replace creativity. That's a very human thing. And we need to teach our students how to use AI, but not stop there, but take it that next step and be creative. So having a process starting with stories, really good stories that show how we can make sustainable impacts while still helping the companies make money will be a sustainable thing in itself, I hope. So this is something that gets me excited anyway.
Yeah.
And we don't know where this is going to go, but I think it's a fun place to start.
And I really do think that this creates a great opportunity for us as teachers to, if this sort of instructional content is structured well, to do the fun part of teaching more and to do the lame part of teaching less. I don't want to give another lecture on phase diagrams either. I'm over it. I'm good, But to sit down with students who are learning this for the first time and to challenge them and to ask them the hard questions and to find where they're going wrong and to correct them and nudge them in productive directions, that's the most fun and rewarding part of this, because you see them learning in real time. And I feel like that's why we're doing this.
So again, we have a large number of our alums who've ended up in industry and are very, easy to get to and ask these questions, and they've all worked on sustainability in their companies. But we only have our alums. Hopefully all of you out there, especially the TMS community, you have graduate students or undergrads who've gone on to industrial careers. Let's find out how we can get access to their stories. So we need your help in getting access to really cool stories about how materials design has really had an impact on sustainability. And so that's kind of the reason we wanted to do this video. This is sort of a call to action to our community to help us. And if you want to start your own podcast and make your own interviews, we'll help you do that, because we just need to have a nice repository of these stories that people can use. And again, the same story can be used. This thing with Paul Krajewski's story, that can be used in the mechanical engineering department. It can be used in, an aerospace department, because they do crimping with aluminum in aerospace. It can be used all over. So one story can actually fit multiple courses at multiple levels. It's just what you're asking the students to do has to be tailored for their ability and their skill set and their knowledge base, so that we don't overwhelm them.
Right, but that's no surprise to us either. We think about the lecture demonstrations that we have. You can do the same demonstration with middle schoolers, with high schoolers, with college students, with graduate students.
That's right.
And expect each of them to get different learning outcomes from it and to challenge them at different levels based on the level of insight that they should have into the system. So,
and of course, we all learn this from physics, because in physics, you only take 4 courses. You just take them over and over and over again.
Until you're broken?
Until you get to Jackson and it kicks your butt. So,
Jackson.
Everything is scaffolded in most science education, and we do the same thing. We don't call it thermodynamics, but we teach thermodynamics when we teach phase diagrams in the introductory course. And then we teach it again at the junior level. Then we teach it again at the graduate level. Right. And the same is true for kinetics and structure and all of these things. But it's really a small set of topics. And but these stories are universal, I think.
That's right. So if you're going to be at TMS, absolutely, please reach out to me and Steve. We'll have our emails in the show notes, and we'd love to connect there. If you have recommendations for people we can talk to, any colleagues you have in industry who have these stories that they'd be willing to share, or if you want to start producing some of this content yourself, we'd absolutely love to connect with you and help make that happen.
And if any of you who are out there listening who have actually had sustainability success in an industry, an industrial process, and would like to tell us your story, please contact us. We'd love to have you on the podcast.
That's right.
So, anything else?
I think that's it.
Yeah. So again, we're hoping you can help us. This has really evolved into something really interesting, I think, and we're excited about it. I hope you are too. I don't think I said, but I'm also going to put in, at the end of this, we'll put in Joel's little segment. We also have another one with John Allison talking about the impact of ICMA and virtual aluminum casting. Mm-hmm. So that's a third one, and that's probably all, but we have many more lined up. And some of you we've talked to, but we haven't contacted you officially yet, but we're coming. So
that's right. We're coming for you. So be ready.
Yep. All right. So thanks for listening, and we'll see you next time.
See you next time.